Hi, my name is Trisha Biswas, and today I'll be talking to you about selectively sharing multipath routes in the Border Gateway Protocol. A little bit about myself. I work with Fastly, which is an edge cloud platform, and my experience is mostly in the area of infrastructure and routing design for cloud networks. So I work a lot with routing protocols, and of course, BGP happens to be the most extensively used one in the internet today. So let's jump right in. The agenda for today's talk includes an overview of the Border Gateway Protocol and what makes it BGP and what makes it the most widely used one in the internet today. I'll then talk about the best path selection algorithm in BGP, and then move on to why sharing additional paths might be useful in some cases. And then we'll talk about some trade-offs about why sharing all additional paths may not be useful, in which case we should do selective sharing of additional paths, and how this can be done with policy-based filtering. Finally, I have a demo to show this feature in action. So to start with, let's talk about BGP. So BGP, like I mentioned, is used all over the internet today. And the reason why is because BGP is designed in such a way that it is very suited towards sharing and distributing routing information. So this is how routing information is distributed between the internet service providers. So the routers are basically devices, and the routers that talk BGP are also known as BGP speakers. So in this case, this protocol is best suited for a network of networks, if you will. So you have, many networks that are connected with one another. And in this case, it's best suited for routing between these networks. So each of these networks is also called an autonomous system. So the autonomous systems can run interior gateway protocol, which is also known as IGP within the system, and exterior gateway protocol between them. So the routing between these different ASs is what we call interdomain routing. BGP neighbors are called peers, and this protocol does not really have any sort of like automatic neighbor discovery like some other protocols do. So you statically have to configure the peers themselves. And this is because peers in the same autonomous system are called IBGP peers, internal BGP peers, and peers in different ASs are called eBGP peers. And there are finer nuances of how BGP functions or how its behavior varies between IBGP and eBGP peers. Therefore, we typically have to configure these statically. And then, so some of these nuances are like if you receive an eBGP route from an eBGP peer, you can share this to either your eBGP or IBGP neighbors. But if you received an IBGP route from an IBGP neighbor, you wouldn't be able to share this with your IBGP peers, but you can only share it externally. So there are other finer nuances between peers within an autonomous system and peers residing in different autonomous systems. So we've been talking about routes. What is a route? So a route is basically a list of autonomous systems along with some other attributes on the path to your destination. So in this case, BGP is most concerned about reaching the autonomous system in which your destination resides. How you get from within that autonomous system to your end node is something which you could do with BGP, but that's not really where it shines. The main goal is to hop between networks and to reach the end autonomous system where your destination is. So the way it does this is by using advertisements. So nodes on the network typically advertise reachability information to various destinations with their peers. And this is also known as a path vector protocol. How this functions is that each node says how how it can reach various destinations, and on the receiving end, nodes receive all these advertisements from their peers, and they try to sort of string together this information and to form like a map of the network, and then run their own best path algorithm on top of that, and then come up with the routing table, which typically has all the routes to reach destinations. So these advertisements, again, have 5 nuances. Like, for example, if a node has advertised a prefix and a path to reach that prefix, and at a later time it changes the path, then that automatically withdraws the previous announcements for that prefix. So for example, if I'm a node and I say that I can reach the destination using some next hop of X, and at a later time I say that I can reach the same destination with the next hop of Y, which is my best path now, my previous announcement of the fact that I could reach it via X is implicitly withdrawn from my peers. So they don't consider that to be a valid next hop from me anymore. And we will use this fact later in the talk, so just keep that in your mind. All right, so I mentioned that once the nodes receive these advertisements, they run their own best path selection algorithm. So let's look at a very small example of how that works. So let's say we have a network of autonomous systems, in this case, A, B, C, and D. To start with, A knows that it has a 0-hop path to itself, and it's directly connected to B and C. So in this case, it has a 1-hop path to reach B and a 1-hop path to reach C. So this is what A advertises to its peers. So let's go in a cyclic manner. So now B receives this advertisement, and it tries to create its own routing table. So in this case, B knows that it has a 0-hop path to itself. It knows it has a 1-hop path to A and D. And using A's advertisement, B now knows one additional piece of information. So B knows that A can reach C with 1 hop. So B now knows that it can reach C over 2 hops via A. So B advertises this piece of information to its peers. So let's see what D knows at this point. So D knows it has a 0-hop path to itself, a 1-hop path to reach B and C, and D now knows that it can reach A using a 2-hop path via B. So it advertises this information. And now when C comes up, it knows that it has a 0-hop path to itself. It has a 1-hop path to reach A and D. And C has also heard from A within this time. So C knows that it can reach B using a 2-hop path via either of A or D. So in this case, once this piece of information is entered, C has 2 paths to reach B. So it uses further selection criteria in order to select one of those 2 paths. In this case, just from the high level look at it, the path from C to B looks like it's equal, but you could use other metrics within BGP, other route attributes, an example of which could be local pref or multi-exit discriminator or MED, to sort of tweak it either way and to make C select either of those 2 paths. So either way, C would run its best path selection algorithm, go over all the route attributes, and then select one of the 2 paths to reach B as its best path. In this case, we're considering C has selected the path via D as its best path, which is marked with a star. Let's look at another example of best path selection. This is a more end-to-end example, if you will. So let's consider that we have a network of autonomous systems, A's 1 through 5, as you can see. And let's consider that you're trying to access some website sitting on your laptop connected to your router, and you are connected to a sub ISP, a smaller ISP, which is denoted with AS0 here. AS0 itself is connected to AS1 and 2 and to the broader network interconnection of autonomous systems. And let's also consider that the website that you're trying to access is the one that's shown at the end there, and it's based off of AS5. So in this case, when you're trying to advertise, when you're trying to access that website, which is based off of AS5, AS5 is the autonomous system that would actually advertise that it has, it can reach the IP address of 123.4.5.0/24. And what AS5 would do here is that it wouldn't really, it may not actually advertise that specific IP address, but it might advertise an aggregated IP address, such as the one shown there, 123.4.0.0/20, which includes the website that you're trying to access. So from the point of view of your ASP or AS0 in this case, it has to basically reach AS5. And the various ways it can reach AS5 are via AS1. So it can go AS1, 2, 3, 4, 5, or it can go take a few other paths using AS1. So it could do AS1, 2, 3, 5, or it could do AS1, 3, 5. So those are all the paths that it can get to AS5 using AS1 as the next hop. Similarly, it could use AS2 as the next hop, and so it could do AS2, 1, 3, 4, 5, or it could do AS2, 1, 3, 5, and lastly, it could also do AS2, 3, 5. So in this case, it would run best path selection, and the shortest paths would win the first level, which would be either of AS135 or AS235. And then there would be some sort of a tiebreaker using those other attributes that I talked about. So it would select one of those two. And let's say that in this case, it picks AS235, and that's where the request would be sent. So that's how BGP would work on a sort of an end-to-end example. So let's talk about additional paths. So we mentioned that whenever BGP computes the best path, it always shares only the best path over a session. It doesn't share all the paths that it has. And this is good for scaling. Like if you have tons of paths to reach destination and tons of destinations as well, this could often reach a very large number. However, you are cutting back on path diversity. So all the nodes that are behind you now don't know all the other ways they could reach destinations. So for example, if you have two nodes A and B in this case, and A's routing table has this route that's shown here, which has two next hops to reach that prefix. A would select one of these as the best path. In this case, it selects the first one as the best path. And what A advertises to B is only that. So it would only advertise one next hop for that prefix to B. And so B, while its routing table is shorter in this case, it has less visibility into the network, if you will, because it doesn't know that there is one other next hop which can help it reach that same destination. So BGP additional paths is specified as an RFC, and this feature allows you to share multiple paths for the same prefix without the new paths implicitly replacing previous paths. Because in traditional BGP, if you have advertisements for this next hop and this next hop, one of these would replace the other because of implicit withdrawal. But the add paths feature helps you to advertise multiple paths to a destination without the future ones replacing previous ones. What this does is it helps achieve faster re-convergence after network failures, because nodes behind the one that has the highest visibility also now know that there are other paths to reach the destination. So let's look at an example of that. So let's say we have this network of autonomous systems. AS1 is your source and AS6 is the destination that you're trying to reach. So in this case, AS2 and AS3 each have computed how they can reach AS6. So essentially AS3 can go AS346 or AS356. Similarly, 2 can go AS246 and or 256. Of these, each of these ASs would pick whatever their best path is and share only that information with AS1. So AS1 in this case only has 2 paths, one out of each autonomous system it is connected to, even though there are actually 4 equal length paths to reach its destination. So all is well. Let's say that AS1 is actually sending its traffic over the multipath, so it's equally distributing the traffic between AS2 and 3, and using all its capacity that it can. Now let's assume that one of these links goes down. So what happens in this case? The link that goes down actually is in the route that AS1 is using, the AS346 route. So in this case, AS1 does not have this information that 2 hops away there's a link that has gone down. And so AS3 would have to actually recompute its best path to be the AS356. And then AS3 would have to relay this information over to AS1, and AS1 would update its routing table. And then, so AS1 essentially has to wait for this whole re-convergence before its traffic can be served. Instead, if we used adpaths, then if all the paths were shared with AS1, when there is a link failure, AS1 would be able to switch to a working path much faster, and it wouldn't have to wait for the re-convergence. So you have, in this case, AS1 has better visibility into the rest of the network, which it won't with traditional BGP. Of course, this comes at a cost. So if you share all paths with all nodes in the network, this would very soon result in an explosion in your routing table. So how can we get like the best of both worlds? So if you look at today's networks, autonomous systems have thousands of prefixes, and there could be thousands of paths to each prefix if every AS used full ad paths. So sharing all of these could mean that you're sharing millions of routes with a peer, and this could potentially overwhelm it. It could reduce its performance. So selective ad paths, which is currently an IETF draft, is a featured extension for ad paths, which allows sending of specific routes for a given prefix based on some additional criteria. So in this case, instead of sharing all the routes from AS3 and AS2, there could be specific other criteria, specific route attributes that you could use in order to select which ones to share and which ones not to share. So if we look at so this is some data that we have from our networks, and we see that the lines here show traffic information from different sites within the Fastly global network. And we see that for most of the sites, a large volume of traffic is served with a very low percentage of routes. So if you look at the volume of traffic, between 80 to 100% of the traffic is served by like 0.1% of the routes that the devices have. Around 90% of the routes is served by less than 1% of the routes that the node has. So this is just to demonstrate that if we enabled ad paths for all the prefixes that are there at a node, we would be sharing hundreds of and thousands of routes. Instead of that, if we could know and we could tell which of these prefixes serves the most volume of traffic, and we share only additional paths for those, then the nodes behind the edge nodes would have that information, that they would have that visibility into the network to allow for faster recovery from failures without getting overwhelmed with millions of extra routes. So the way we can do this selection is based on BGP policies. So routes can be filtered based on any of the attributes. So if you look at this example route from a node, it has all these attributes, like it has, of course, who the next hop is. So this route has two next hops here. So it has who the next hop is, what the AS path is, what the med is, what local pref is, what extended communities it has attached. And these are standard BGP route attributes. And we could use any of these to define, which ones we want to share. So at the very least, we can say that for these prefixes, for these destinations, give me all the additional paths, if those are destinations that we have to reach out to often. Or we could say something like, if it has this special extended community attached to the route, then I want additional paths for this route. And so we can look at that with a demo. So on the left, you have a node that has full visibility into the network, and it knows all of the external facing routes. And on the right, you have a node that is behind the edge node, if you will. So it doesn't really have that advantage of full visibility into the network. So if we look at this route, we see that from the edge node, it has two paths to reach the prefix shown there. And these are external next hops that it has on its end. If we look at the same route on the device on the right, we will see that it has one next hop. So in this case, whichever node was picked as the best path by this first router is what is shared with the second router, B in this case, and that's what it has. So if we look at the count of routes in this case, let's say, then we see that the node on the right has 159 routes right now. And so this is just with usual BGP routing. If we were to enable add paths or additional paths, then we can see what happens. So in order to do that, and we use Bird in our routing stack. So this is what Bird's config looks like. And Bird happens to be an open source routing stack. So I would configure that, and then it takes a little bit of time to reconverge. So I guess it's still converging. So we have enabled add path on the receiving end now. And if we look at the configs on the sender side, then we'd see that we already have add paths DX enabled, which is the add paths transmit end. So now if we go look at the route count, we see that so earlier on we had 159 routes, and now we got 162 routes. So we got a few extra routes by enabling add path. So this is if we enable add path for all sessions. In this case, we had a few extra routes, so that's what the node on the right sees. But now we can go and add in more selection criteria in order to do the to selectively share these additional paths. So going back to the config, so we have something called filter in Bird, which is basically a construct that allows you to filter out routes as you will. The filter currently had nothing but accept, so whatever came in it through the filter would be accepted. What I'll do right now is add some policies. So this is a very basic policy where I'm saying that if it's a best path, or preferred is the keyword we're using here. If it's the best path or preferred, then accepted, and in all other cases, rejected. So with that, if I go and run a configure, then we see that the count of routes has once again dropped to the 159 that we saw before. So even though we have add path enabled, our selection criteria says that only share the best path, which is nothing but your plain vanilla BGP behavior. So we go back to the original number of routes that we saw, which is 159. And if we look at that route we were looking at originally, it still has one next hop. If I actually go and remove that once again, we'll see that the node on the right gets both the next hops. So if I do that and run a configure, and then on this end, I try to see the route, I'll see that here I have the two next hops, which I saw same as what I had seen on the left side before. So if I look at the same route here, two next hops, and both the next hops get propagated to the node on the right because I've enabled add path. So now let me go back to adding some more policies in there. So for example, I could say something like if it's best path, or if the prefix is so-and-so, then accept it. So then share all additional paths for only that 200 prefix, and for all other prefixes, only share the best path. So, and that I would expect it to add exactly one extra route on top of the 159 that we had seen. So I configure that. On this end, I would still see the two next hops. And if I do a route count, in this case, I see 160 routes. Remember, we had originally seen 159. So this adds exactly one more route for that, exact match prefix that we specified. Now, if I go back to my configs, and I can do slightly more involved selection criteria. So I could say something like if it's best path, or if the network is so-and-so, and the, and it has an extended community, which is of this, of that, then share the additional path. So in this case, the route in question, both the next hops have that extended community. So this should not really change my count or the next hops I see. So if I see that, that remains the same. And if I see a route count, I still have 116 there. Now, the last thing that I wanted to show was that we could also add in a bunch of other prefixes there. So we could do something like, if it's best path, then share. Otherwise, if the prefix belongs to these array of prefixes, in this case we have 2 specified, then accept, and otherwise reject. So you could specify a bunch of prefixes for which you want additional paths, and you don't want add paths for anything else. So if I do that, in this case, I would expect the route count to go up to exactly 2 more than our original. So it should be like 161, because now I've specified 2 prefixes and each of them have 2 next hops. So yeah, that's pretty much it. You can use any of these route attributes to sort of specify what to cater to exactly what you need and how much you want to share and how less you want to tie it down to. So going back to the presentation, so I'd like to conclude with some of the key takeaways from this. So BGP ad paths helps achieve faster reconvergence, but because you're sharing all your additional paths, it's like a 0 or 1 transition. You don't share or share all. This can now affect the overall performance of the peer because of the large number of routes that you're advertising. And we also found from experiments within our network that even though autonomous systems have hundreds of thousands of routes, only a few hundred are actually serving most of the traffic, and likely those are the only ones that are worth sharing. So you could potentially use that information and use and craft some sort of a selection criteria that you want to share these additional paths for. So this extension of the selective ad paths helps achieve the best of both worlds by leveraging BGP multipath without having to overload your peers. With that, thank you for watching. I'll be happy to take any questions you might have.